this laboratory activity, we were tasked with creating a model of a single-phase two-winding transformer using MATLAB Simulink. The transformer was configured using the following parameters. These specifications were entered into the Simulink model to represent the behavior of an actual transformer under operating conditions. After successfully building and verifying the transformer model, we conducted a performance analysis by varying the load resistance connected to the secondary side. The purpose of this experiment was to observe how changes in load resistance affect the transformer's output, voltage, and overall performance. Several resistance values were tested and corresponding output voltages were recorded and analyzed. Based on the simulation results, we observed that increasing the load resistance caused a slight increase in secondary output voltage. This occurred because a higher resistance drew less current from the transformer, resulting in smaller voltage drop across the transformer's internal winding resistance. On the other hand, decreasing the load resistance led to a slight reduction in output voltage. Low resistance loads draw higher currents, which increased the voltage drop within the transformer and caused the secondary voltage to decrease. Through this activity, we gained a better understanding of transformers' operation and the relationship between load conditions and voltage regulation. The simulation demonstrated that although the voltage variation were relatively small, load resistance has a noticeable effect on transformers' performance. In our second laboratory activity, we performed an open circuit test on a single-phase transformer using MATLAB Simulink. Similar to the previous activity, we first created a transformer model using the given parameters. After successfully building the model, we ran the simulation with the transformer operating under no load conditions, meaning that the secondary side was left open and no external load was connected. During the simulation, we measured the voltage and current on the low voltage side of the transformer. Using these measured values, we calculated the transformer's apparent power and reactive power, which helped us analyze its no-load performance. Through this experiment, we gained a better understanding of how an open circuit test is performed and why it is an important procedure in transformer testing. We learned that this test is primarily used to determine the transformer's core or iron loss and magnetizing current. Since the current drawn under no-load condition is relatively small and the copper loss are considered negligible, overall this activity demonstrated how open circuit testing can be used to evaluate the efficiency and operating characteristics of a transformer without connecting a load. In our third laboratory activity, we performed a short circuit test on a single-phase transformer using MATLAB Simulink. We first built the transformer model using the given parameters. After completing the transformer model, we conducted a short circuit test by shorting the high voltage side of the transformer. A small AC voltage was applied to the opposite winding. Unlike a normal operating condition, only a low voltage was required because the secondary winding was short-circuited. The input voltage was gradually increased until the transformer reaches its rated current of 10 amps. Once the rated current was achieved, we recorded the voltage, current, and power measurements from the simulation. These values were then used to calculate the transformer's equivalent circuit parameters, including the equivalent resistance, equivalent leakage reactance, which represents the transformer's copper loss and leakage impedance. Through this laboratory, we learned the purpose of procedure of the short circuit test. We understood that this test is mainly used to determine the transformer's equivalent impedance and copper losses, while the core losses remain negligible because of low applied voltage. Overall, this experiment helped us better understand how short circuit test is used to evaluate the internal characteristics of and performance of a transformer. In our fourth laboratory activity, we studied the voltage regulation of a single-phase transformer using MATLAB Simulink. We first built the transformer using the given parameters. After successfully recreating the transformer model, we investigated how different load conditions affect the transformer's output voltage. We varied the load resistance from no load condition to 0.8 ohms and 0.5 ohms, then observed and recorded the corresponding output voltages. By comparing the result at each load resistance, we were able to evaluate the transformer's voltage regulation and overall performance. From the simulation, we observed that the transformer delivered its highest output voltage under no load condition. As the load resistance was decreased, the transformer supplied more current to the load, resulting in a gradual decrease in secondary voltage due to voltage drop across the transformer's internal impedance. This demonstrated the effect of loading on transformer performance and voltage regulation. Through this laboratory activity, we learned that voltage regulation is an important measure of a transformer's ability to maintain a constant output voltage under varying load conditions. A transformer with a good voltage regulation experiences only a smooth change output voltage as the load changes, making it more efficient and reliable for practical electrical applications. In our fifth laboratory activity, we studied the efficiency of single-phase transformer using MATLAB Simulink. We first created a transformer model using the given parameter and then ran the simulation to analyze its performance under operating conditions. The main objective of this activity was to determine how efficiently the transformer transfers electrical power from the primary winding to the secondary winding. To do this, we measured the input power and the output power of the transformer from the simulation results. These values were then used to calculate the transformer's efficiency, which in the ratio of power output to the power input expressed as a percentage. Although transformers are considered highly efficient electrical devices, they still experience power losses during operation. These losses are mainly caused by copper losses in the windings due to the resistance and core losses resulting from the magnetic properties of the transformer core. Because of these losses, the output is always slightly lower than the input. Through this laboratory activity, we learned how to evaluate transformer performance by comparing the input and power output. We also gained a better understanding of the factors that affect transformer efficiency and why minimizing power loss is essential for improving the overall performance and reliability of electrical power systems. In our sixth laboratory activity, we studied the parallel operation of single-phase transformers using MATLAB Simulink. We first built a model consisting of two identical transformers, each with a rated voltage of 220 volts, a rated power of 1 kVA, a turns ratio of 1 to 2, a primary winding of 0.1 and a secondary winding of 0.05. After completing the transformer model, we ran the simulation and measured the output power of the parallel transformer system. We then varied the load connected to one of the transformers to observe how the load was shared between the two transformers and how this affects the overall performance. By comparing the simulation results under different loading conditions, we observed how the transformers work together to supply the load. We also saw that changes in the load influenced the amount of current and power carried by each transformer, while the total load was shared between them accordingly to their electrical characteristics. Through this laboratory activity, we learned that operating transformers in parallel allows them to share the load, increasing the overall power capacity of the system. Parallel operation also improves system reliability and flexibility, since one transformer can continue supplying part of the load if the other is removed from the service for maintenance or development. In addition, using transformer in parallel makes it easier to accommodate future load growth by adding more transformer capacity without replacing the entire system. In our seventh laboratory activity, we learned how to model and analyze a three-phase transformer bank using MATLAB Simulink. We first created a new Simulink model and added three-phase voltage source. with an amplitude of 480 volts and a frequency of 60 Hz. Next, we added a three-phase transformer with 2 to 1 turns ratio, 0 degree phase shift, and a rated power of 30 kVA. Finally, we connected a three-phase load with a power factor of 0.8 lagging to complete the system. After building the model, we ran the simulation and observed the output voltage and waveform of the transformer bank. We then repeated the simulation by varying the load from 0.2 per unit up to 1 per unit up. This allows us to compare the transformer's performance under different loading conditions and observe how the output voltage changed as the load increased. By analyzing the simulation result, we found that the transformer bank maintained a relatively stable output voltage under light loads, while a slight voltage drop occurred as the load approached full capacity. This demonstrated that the concept of voltage regulation and how increasing the load affects the transformer's performance. Through this activity, we learned how the three-phase transformer bank operates in a power system and why it's widely used for transmitting and distributing electrical power. We also gained a better understanding of how the effects of load variation and voltage regulation and the importance of maintaining stable voltage for efficient and reliable operation of three-phase electrical system. In our 8th laboratory activity, we explored the open delta VV connection of single-phase transformer using MATLAB Simulink. We first created the transformer model by configuring the required parameters, including two windings, a delta-delta winding connection, a three-leg core, and a fixed magnetic flux model. We also specified the primary and secondary winding resistance, leakage inductance, and magnetizing inductance before setting the simulation time to 0.02. After completing the model, we connected a 240 volts 60 Hz sine wave source to the primary winding and attached a scope block to the secondary winding to observe the output voltage waveform. We then ran the simulation and analyzed the waveform to evaluate how the transformer performed under an open delta configuration. From the simulation result, we observed that the transformer was still able to produce a balanced three-phase output even though only two single-phase transformers were used instead of three. However, we also learned that the open delta connection has lower power capacity compared to closed delta connection, making it more suitable for temporary operation or for supplying smaller three-phase loads. Through this laboratory activity, we gained a better understanding of the operation advantages and limitation of the open delta connection. We learned that this configuration provides a practical and economical solution when one transformer is unavailable due to maintenance or failure, while still allowing the system to continue supplying three-phase power, although at a reduced capacity.